All right, guys. So this short video is just going to be a walkthrough of the end of the Unit 6 limiting excess reactants and BCA chart notes. It's going to be the last two examples on that from those notes. All right. So the third example says, what mass of hydrogen is produced from the reaction of 50 grams of magnesium and 75 grams of hydrochloric acid? How many grams of excess reactant are left over? So there's a couple of things going on here. So first, we want to find the mass of H2 that was produced, right? This deal. So if we look at our chart, at our balance equation in our chart, H2 is over here, it's a product, right? So the amount of H2 that's produced from the reaction is going to be down here in this spot. It's after the reaction's done, the amount of H2 that's made is going to be, excuse me, down here. Now, remember, all the numbers in the chart are in moles, so we'll have to do a little converting, but that's that. Now, how many grams of excess reactant are left over? So that is going to be a little different part. So let's hold off on that. Okay, let's start with this first part here. So in order to fill out the chart and stuff, we need to find the limiting reactant, right? So, but before we can find the limiting reactant, we need to get our moles that we're starting with. We're not starting in moles on this. They're starting in grams. So the first thing we're going to do is we're going to convert 50 grams of magnesium into moles of magnesium. So grams of magnesium on the bottom because it's on the top here, turning it into moles of magnesium. This conversion, grams to moles, 1 for the mole, the molar mass for the grams. Magnesium is just Mg, there's no Mg2 or anything on it, so it's the mass, so it's 24.3. Okay. So do the math on this. Let's see. So 50 divided by 24.3, and we get 2.058. I'm rounding it a little bit there, moles. So that's the moles of magnesium that we're starting with, right? So up here, magnesium, the moles that we're starting with, 2.058. Not putting moles in the chart because remember the entire chart is always in moles. So, all right, now we need to do the same thing for the hydrochloric. We need to find out how many moles we're starting with. So we take 75 grams of the hydrochloric acid and we convert grams of hydrochloric acid to moles. It's 1 for the mole. Hydrochloric acid, chlorine is 35.5. There's only one of them. Hydrogen's 1, so it's 36.5. And we get 2. Oh, that's almost super close to exactly the same. 2.055 moles of hydrochloric acid. So that's what we start with up here. Now, how do we find the limiting reactant? To find the limiting reactant, we take the moles we start with. So this is for, we need to know, it doesn't ask for the limiting reactant, but we need that to do the rest of this. Sorry, before I do that, before row, on our product side, remember the products on the before row are always 0 because we haven't done the reaction yet, so we don't have any product. It looks like this. All right. Now, we need to find the limiting reactant to do the rest of this. So to do the limiting reactant, we take the number of moles for each thing and divide it by the coefficient. So we take the 2.058 moles of magnesium divided by the coefficient in front of magnesium is nothing, so it's a 1. So it's 2.058. For the hydrochloric, it's 2.055 moles of the hydrochloric divided by the coefficient in front of the hydrochloric, which is 2. So this comes out to be 1.028. I'm rounding there to that. 1.028. Oh, sorry, not on the screen there. There we go. Okay. Now, after we've taken the moles divided by the coefficient, we compare these, right? So we are comparing, and the smaller one indicates what the limiting reactant is. So our limiting reactant, this tells us, this is a smaller one, this tells us that our limiting reactant, let's write it down here, I guess. Limiting reactant is HCl. Okay, so at this point, the next thing we're going to want to do is fill in the change row. Okay, now the change row, again, you don't have to, what I put in red in here, you don't have to put in the chart, but I'm doing it so you can see where stuff is coming from. So the change row is the coefficient times the limiting reactant number, the number that showed you what the limiting reactant is. So, hold on, there we go. Okay. So, our coefficient for Mg is nothing, so it's a 1. Our limiting reactant number was 1.028. Okay, so 1 times 1.028 is just 1.028. For hydrochloric coefficient is 2 times 1.028. Remember, it's always times the smallest number. You just always use that times the coefficient. So now this gives us, like, if we were to take that number, like 2 times 1.028, we actually get 2.056. Okay, and I'm going to show you something about that in a second here. And we do the same thing for the products over here. So there's nothing here, so it's 1 times 1.028. So that is just going to be 1.028, right? And then the same thing for the H2, nothing in front of that, so it's 1 times 1.028. All right, and again, you don't have to show the multiplying on this. I'm just doing it so people know where the numbers come from. All right, now our after row. The after row, remember, is real simple. You subtract reactants before minus change. So we subtract and we add products. So 2.058 minus 1.028 gives us 1.030. Okay. Now, if we subtracted this, okay, so this is what you would see on your calculator. Okay, you see negative 0.001. That's just because of rounding. Okay, if you look, like 2 times 2 times the limiting reactant one should just undo this. So it really is like 2.055. So if you put 2.056 in there, that's fine. Just know that if you get a number like this, like super close to one, like it's actually, or super close to 0, it's actually just 0. It's just because of rounding that it wasn't perfectly on 0. So you can just put a 0 there, which again makes sense with our information because we said that the limiting reactant is hydrochloric, which means that runs out. So after the reaction is done, that should be a 0, which it is. Okay, now, okay, and then these are adding, those are just zeros, so these are just copying the change row down again. All right. So at this point, we have our after amounts, remembering all the numbers in the table are in moles. Okay. So let's go back to our problem and see what we're trying to get here to kind of refresh our memory. So one thing we wanted was mass of H2, right? So if we look here, this is where we identified, this is where the amount of H2 that we had it after the reaction was done, this is where it would be. But don't forget, this is in moles. We want the grams. So what we're going to do down here is we're going to do a conversion from 1.028 moles of H2. And we are going to convert moles up here, so moles on the bottom, moles of H2, convert to grams of H2 because we want to put it in mass. Okay, moles to grams, 1 for the mole. The gram is the mass times the atoms, and you add them together if there's more than one element. Here there's not, so it's 1 times 2, 2. Moles have canceled, we're in grams, which is what we want. We do the math. We get 2.056. Now, significant figures, we would technically use like the limiting reactant substance and those. So you can just look up here. I try to not make that too difficult. So like it's 3 and 3. So you have 3. So from what my numbers would be, and I'm not going to be super picky on this. I'm not going to be real picky on, as long as you're close there. So 3 significant figures would be 2.06. And our label grams of H2. So this answers what is the what mass of H2 is produced. This part right here. Okay. We're not done yet. Close, but all right. We had another part of this, which was how many grams of the excess reactant are left over. Okay, so what does excess reactant mean? Well, that's the reactant that wasn't used up, the one that there was more than enough of. So what's our excess reactant now that we know what our limiting reactant is? Our limiting reactant was hydrochloric, which means our excess reactant is magnesium. That's the one we had some left over. How many grams of that were left over? Well, that's here, right? Except, again, the entire table is in moles. So we had, after the reaction was done, we had 1.030, that came from this minus that, right? 1.030 moles of Mg, and we're going to turn that into grams. Moles of Mg to grams of Mg. Okay, again, mole to gram, 1 for the mole. This is just Mg, so nothing to multiply by, so it's 24.3. Okay, so we do the math. And 3 significant figures gives us an answer of 25.0 grams magnesium. Oop. So how many? Sorry. Okay. So that's how many. That's how much of the excess reactant was left over. So that answers both parts of that problem. Okay. All right. Last example. Silver nitrate and sodium phosphate are reacted in equal amounts of 200 grams each. How many grams of silver phosphate are produced? What is the mass of the excess reactant left over? So I'm going to highlight again, just so we keep things organized. I'm trying to find grams of silver phosphate, right? And also, later on, mass of the excess reagent, same as reactant. Okay. So this is going to be very similar to the one that we just did in terms of the steps we need to take. Okay. Silver nitrate and sodium phosphate are reacted in equal amounts of 200 grams each. So to get the numbers in the BCA chart, we need to turn grams into moles, right? So I'm going to start 200 grams each. So I'm going to start with 200 grams of AgNO3, the silver nitrate. And I'm going to turn grams of AgNO3 into moles AgNO3. Okay. Moles to grams, again, 1 for the mole. The gram, silver. Okay, so this is silver, there's one of them, so 107.9 for the silver, plus 1 times the nitrogen, which is 14, plus 3 times 16 for the oxygen. So we get 169.9 for the grams of AgNO3. All right. Okay, so we get 200 divided by that, and we get 1.177 moles of the AgNO3. So this is going to go up here, the before for the AgNO3, because it's just, we started with 200 grams. 200 grams is 1.177 moles. So 1.177 for the moles for the AgNO3. Now we're going to do the same thing for the Na3PO4. 200 grams, that's what it told us we had, of the Na3PO4. Same idea. We're going to go from moles of the Na3PO4, and we're going to turn it into grams. Grams of the Na3PO4. So doing the math on this would be sodium 3 times 23 plus 1 times phosphorus, which is 31, plus 4 times 16 for the oxygen is a total of 164. Okay. So 200 divided by that gives us 1.220 when you round it, moles of the Na3PO4. All right. So that's the moles of the Na3PO4 that we're starting with, 1.220. Okay. Before for the products, always zeros. Right? Okay. So at this point, excuse me, we are going to We need to find the limiting reactant, even though it didn't ask us. We need to know which one runs out first. So our limiting reactant. Now I'm going to do this here. I'll do the limiting reactant step in a different color here. I'll do it in a pink color. But I'm going to just save a little space. I'll show you kind of how we can do that. So these numbers are the moles that we start with, so they go up here in the before. Then to do the limiting reactant, you take the number of moles you start with divided by the coefficient, right? So the number of moles of AgNO3 that we start with, so this is for to find the limiting reactant, take the number of moles you start with divided by the coefficient. So we're going to take this divided by the coefficient. We get 0.392. Okay, same thing with this one. We're going to divide it by the coefficient, which for that one is just 1. So this is 1.220, right? Now, compare which one is smaller. This one is smaller. So that tells us our limiting reactant is the AgNO3. Now again, it didn't ask us what the limiting reactant is, but in order to do the rest of the problem, we need that. Okay, so the limiting reactant is AgNO3. Now, how does that help us? Well, that helps us on the change row. The change row, you take coefficient times the limiting reactant number, the smaller number that told you what the limiting reactant was. So look at these numbers. What was a smaller one? This one. So you take the coefficient for each one. So 3 times 0.392. Here, this is 1 times 0.392. 1 times 0.392. 3 times 0.392. And again, I'm showing you this so you know where the numbers come from. You don't have to show that work. By the way, just in case anybody's confused, you do have to show all the other work though. Literally everything else. There's nothing else on here that you can leave off. Okay. All right. So change row, multiplying these. So 3 times 0.392 gives us 1.176. Okay, 1 times that is just 0.392. 0.392, and this is 3 times it, so it's the same as over here, 1.176. Now, subtract to get your after row, subtract reactants, add products. So here, now remember, so this actually would come out to be 0.001, but remember, that's like the limiting reactant, so it's really coming out to be 0. Double check, is that our limiting? Yep, that makes sense. So it doesn't guarantee we're doing it right, but it's a good indication. So 1.220 minus 0.392 gives us 0.828. This is 0.392 and 1.176. All right, we're doing well. We've got our after. So remember, whole chart always in moles, right? So if we look, let's go back to our problem. We need grams of silver phosphate. So silver phosphate is, silver is Ag, phosphate is PO4. So right here, this is silver phosphate. Okay, so where is the amount of that that's produced? Well, we're going to use this here, right? It's not the actual answer, but that is the amount that was made, but in moles. So we need to turn that into grams. So we're going to do conversion. Hopefully you guys can still see all this. You're going to start with the 0.392. That's moles of Ag3PO4. And we're going to turn that into what we want, which is grams of silver phosphate. So conversion, whatever's up here on the bottom. So moles Ag3PO4. We're turning it into grams of Ag3PO4. Moles to grams, 1 for the mole. You gotta multiply times the number of atoms, the masses, and add them up. So silver Ag is 107.9 times, we got 3 of those, plus 1 of the phosphorus, so it's 1 times 31 is 31, plus 4 times 16 for the oxygen, gives us a total of 418.7 grams of Ag3PO4 for 1 mole. Moles Ag3PO4 cancel. We're left with this, which is what we want. Just do the math, and I'm going to put the answer down here because I need to save room for something else. So 0.392 times 418.7 gives us an answer of, and significant figures are 3 because there's a decimal there, so 164 grams Ag3PO4. That is the grams of silver phosphate that was produced. Okay. So that is this. All right, we still have one thing left. What is the mass of excess reactant left over? So excess reactant is the one that was not used up. So in this case, it's the Na3PO4 was not the living reactant. So this, again, now remember, this is not mass, it's not grams, it's the moles. So we've got to do another conversion, just like we've been doing. Yes, there's a lot of work on these. Moles Na3PO4. And we're going to turn moles of Na3PO4 into grams. So Na3PO4, 3 times Na is 23, plus 1 times phosphorus is 31, plus 4 times 16 equals 164. That's weird. 164 for that. And then we just do the math. So 164 times 0.828. We get an answer of significant figures of 3, so 136. Our label grams Na3PO4. And this is the mass of the excess. So this is the amount of the sodium phosphate that was left over that was not used up in the reaction. Okay. There you go. All right. I know it's a lot of work, guys. That's why you don't have as many of these on the worksheets usually. If you guys have questions, please remind text me, message me in Google Classroom, whatever. Do not come in not having this done and being totally confused. okay, because you'll fall really far behind. All right, good luck. I will talk to you all later.